We're going to take the electric dipole perturbing Hamiltonian now and look at photon emission and absorption. So in annihilation and creation operator form, we've already figured this out. This is our perturbing Hamiltonian. For simplicity now, we're going to presume the simplest conceivable case that we've only got one electron and that it only has two states of interest to us. So here's one state and here's another. State 1 will be our lowest electron state, lowest energy, and it will have energy E1. And state 2 will be our upper electron state, and it will have a larger energy E2. We're going to look over the next couple of units at three possible processes here. So the first will be photon absorption, and that's what we'll look at in this unit. And we'll come back in subsequent units to look at spontaneous emission, which is a process in light bulbs and the sun that dominates, and stimulated emission, which is the process that we see in lasers. So let's start with photon absorption. Suppose that the electron is initially in state 1, and that's the lower state. So here's the electron in that state, figuratively. And we presume also that there's one photon in a specific mode, which we'll call lambda 1. So here's our photon, figuratively, in this mode lambda 1. And we also presume for simplicity here that there are no photons in any other modes. We can come back later and understand what happens when we have many photons in many different modes. Then the initial state of our system can be written in the following form. So we start with the empty state. We use a creation operator for mode lambda 1 to put one photon in this mode. And we use a creation operator for state 1, electron state 1, this fermion creation operator B1. So this is a way of explicitly writing this specific state of the system. And of course, that corresponds to a list of occupied states. In this case, for fermions, it would just be one electron in state 1. And this corresponds to our list of possible boson states here for our specific situation, and that is just one photon in mode lambda 1. Now, this state is going to have an energy that is the sum of this electron energy here and the sum of the energy associated with one photon in that mode. And we know what that is. That's h bar omega lambda 1. From now on, for simplicity, we're going to omit the 0-point energy of the harmonic oscillator. That's the additional 1/2 h bar omega lambda 1 terms. And we've already been omitting that in some of our discussions here. That merely corresponds to a choice of the energy origin, and it doesn't make any difference to this analysis we're going to do here. Now, in our perturbation theory result that we figured out, presuming that we started in a specific starting state S, and we were looking at the change of the expansion coefficient in state Q, we had this expression from time-dependent perturbation theory, first order time-dependent perturbation theory. And as time evolves then, to have any non-zero result for the subsequent amplitude of CQ, so integrating this up, presuming it starts at 0, and looking at this as a time rate of change of it, as required, therefore, for any transition of the system to state Q from its starting state S, we must have that this matrix element is not 0. If this matrix element is 0, the rate of change of this amplitude of the state Q is going to be 0, and hence we're not going to get any transitions into that state. Now, in this matrix element, we have, starting out with just the right-hand 2/3 of it, we see the perturbing Hamiltonian operating on this state here. And that is the following set of operators. So here's our perturbing Hamiltonian, and then here's the state on which we're operating. So this is the state with one photon created in lambda 1 mode, and 1 electron created in electron state 1. Now, if we look at this sequence of operators here, we can multiply it out if we like somewhat, or move things around. And we know, for example, that the fermion and boson operators commute, so we can pull this operator out to here, so we do that. And then we can multiply out these boson operators to group them together into 2 pairs here. So that's A lambda times A lambda 1 dagger, and this is A lambda dagger times A lambda 1 dagger, and that's from the product of this and this, and we've got a minus sign here. Well, we can keep on going with this, and now we're going to use our standard manipulation. We want to do whatever manipulations we can that will push annihilation operators to the right. So we've got 2 pairs here where we can do that. We have this pair for the fermions. We're going to use the fermion anti-commutation relation to turn this pair of operators into a delta K and 1 minus B1 dagger BK. So we've taken this pair of operators, we've used the fermion anti-commutation relation to make that substitution. This delta K1 is a Kronecker delta, and it will be 1 only if the state K of interest here happens to be state 1. Otherwise, it will be 0. And then over here, we have one situation where we can swap these 2 operators. So writing out this using the commutation relation for boson, annihilation, and creation operators, we substitute for this pair with this expression here. So note that we've been able to swap these 2 operators. We've acquired a Kronecker delta here, which will be 1 if mode lambda is the same mode as mode lambda 1. And we have this pair of annihilation and creation operators here with the annihilation operator on the right. Now, we can multiply that through a bit further here, because each of these terms with an annihilation operator on the right will simply disappear, because that annihilation operator is operating on the empty state, and similarly this annihilation operator is operating on the empty state. So anything associated with these 2 terms will simply disappear. So in this term here, since this one disappears, we're just left with the delta K1, so we can bring that out. And in this term here, this disappears, so we're just left with these 2 terms, which is what we see here. And so just separating that out a little bit for convenience, we obtain 2 terms, therefore delta K1, delta lambda lambda 1, and Bj dagger operating on the empty state. And similarly, we have Bj dagger delta K1. So here's the Bj dagger and the delta K1. We've got a minus sign, and we have this pair of operators here. So all of the operators that we found up here in the right-hand 2/3 of the matrix element we want to evaluate can be rewritten in this form when operating on the empty state. With this result that we've just figured out here, in this part of the matrix element we're interested in, there are therefore only 2 possible choices for the state Q in the state we're going to put on the left-hand side here, actually, that will give us non-zero results when we come to evaluate the entire matrix element. So we've managed to write all these operators out like this, and they're the ones that are in here, and hence there's only 2 choices of the state Q to put on the left here, 2 choices of fermion and boson occupation lists to put on the left that will give us non-zero results. Either we choose this state to be Bj dagger operating on the empty state, or we choose this state to be Bj dagger, A lambda 1 dagger operating on the empty state. Why do we know we can only choose these 2? Because those are the only 2 states on the right. So when we choose states on the left, we have to choose them to be either one of these 2 possibilities, and of course then we take the Hermitian adjoint on the left. If we choose any other such possibility, we will simply get 0 as the result of the matrix element. Because all of these various states that we could choose, other states we could choose with different combinations of annihilation and creation operators, would be orthogonal to all of these states here. Hence, in order to get a non-zero matrix element, because we figured out that the right-hand 2/3 of this matrix element was written like this, the only two choices we can make for states on the left with definite occupation numbers in them are either that we choose this state to be essentially this one, or we choose this state to be essentially this one. And of course, this is the Hermitian adjoint on the left, but these are the states whose Hermitian adjoint we would take to get this element on the left here. So let's consider the first possible final state here, and that would be the one where we are saying the final state that we're interested in, state Q that we're interested in, is the one that corresponds to just having an electron in some state J. We've only got two choices for these, but we'll have to look at both of them. J could be either 1 or 2, but we have an electron in state J and no photon anywhere. So that's our first possible final state that we're going to look at here and see what happens when we work through the rest of our derivation. And that is the state, as I said, with one electron in state J and no photons in any modes. Now, this state will have an energy that is simply the energy associated with this particular electron state, whatever that is. So it might be that J could be 1, in which case this would be E1, or possibly J could be 2, in which case this could be E2. Having made that realization here, then we can actually put that result into our explicit statement for CQ dot 1. So we have now the EJ in here. And what we're left with over here, because we've made this choice of final state, is just to evaluate this matrix element of that state with itself, which of course is 1, because this is a normalized state, and of course so also is this Hermitian adjoint, and they're the same state, and hence this is 1. So our Kronecker deltas take care of this summation, leaving us only with this possible term. So K has to be 1, because we've got a Kronecker delta K and 1, so here's the 1 down here for K. And the photon mode lambda has to be specifically the one lambda 1, where there was originally a photon. So that's the lambda 1 down here. Now, to complete this, we need to look also at the Fermi's golden rule derivation. We've looked already at the matrix element, and we found under what conditions perhaps the matrix element is going to be non-zero, and there's one more we'll come back and look at for that. The second condition we have in our Fermi's golden rule we're going to get to is that the energies have to be right. So let's repeat our Fermi's golden rule derivation just to remind ourselves of how we do that, and we'll do it in the current notation. So here we have our statement again that we've got to so far. We know that this is going to be the energy of the system we have to think of overall. The energy difference comes in here. And we're going to be working to figure out what CQ is, CQ1. So we integrate over time. And by definition, we choose that to start with, this amplitude is going to be 0. In other words, we start out with the system not being in this state Q, whatever that is. And since we regard the system, therefore, as starting in this specified initial state at t equals 0, our state S, whatever that was our starting state. And we've chosen a specific choice here for that starting state that we're going to work with. Hence, integrating from t equals 0 to t equals t0 some time or other, we have, with this equation here, we integrate it up. We simply integrate the exponential. That brings a term like this onto the bottom line. And we're left with this as the result of performing that integral. So integrating this term formally, we get this result down here, integrating from t equals 0 to t equals t0, with the presumption that CQ 1 of 0 was 0. The system started out by not being in that state Q. So in this expression here, we can simply rewrite that. We take out a factor e to the I ej minus E1 minus h bar omega lambda 1 T naught over 2 h bar, in other words, half of this exponent. And that splits us into a symmetrical pair, which turns out to be a sine function. This is just a simple algebraic rearrangement here. So, taking the modulus squared of this to find the probability now that we find the system in the state Q at time t naught, we get this expression, just the modulus squared of that expression. And we can rewrite that slightly if we like. We can take out a factor t naught out the front, and we can put that on the bottom line here. Now, a function like this is a sharply peaked function near this particular value of these arguments, all of these being equal to 0, and it has unit area when integrated over this energy argument here. So that's based on the fact that the integral of this function from minus infinity to plus infinity is just pi. Hence, in the limit of large T naught, this object can be replaced by a delta function. It's a sharply peaked function near a specific value of an argument that has unit area. And in the limit of very large T naught, it gets as sharply peaked as we like, while still keeping the unit area. So this expression here then can be rewritten, turning this into a delta function, and hence we have the expression that is essentially our Fermi's golden rule with one final step to complete. So this gives a steadily rising occupation probability for this state Q as we consider longer and longer times T naught. So therefore the transition rate will be this probability divided by the T naught, and that gives us our transition rate here. So we've re-derived Fermi's golden rule rather quickly here. And this is our transition rate. It has the matrix element in it that we've been looking at, and it also has this Dirac delta function giving us some constraints on energies here. Well, we go back to thinking about our energy levels and our photon and our electron here. Now, we were looking at a state where we were going to end up with the electron being in a state J, and J could be either 1 or 2. We were only looking at these two levels. So if we look at the case of J equals to 1 for the final state, this delta function here is E1 minus h bar omega lambda 1. Well, that's going to vanish for any finite photon energy. So the only final state Q from the two that we were looking at that will give a transition rate is if we have J equals 2, with the corresponding restriction that the energies have to match. So this is saying that if we come in with this photon energy here that is equal to the separation of these two energies, then we can get transitions. So our process, therefore, is as follows. We start with one photon in mode lambda 1 and an electron in state 1. That was our choice of starting state, as we have here. And we finish with no photons and the electron in state 2. That was our choice of final state. The only choice we could make for J was J equal to 2. So the final state we had from the one that we were looking at, the only possibility was that we ended up therefore with no photons and the electron in state 2, not state 1. So that's moved us into the state where there are no photons and the electron is in state 2. This is a normal absorption process. And we see now that it requires the destruction of the photon in the process. We didn't presume that here. We presumed that we were starting out with an electron in state 1 and we had a photon here. And we just concluded that the transition that will get us into state 2 also means that we destroy the photon in the process. That has come out of our operator algebra here. Now, from our operators, the other final possibility we were looking at, other than just bj dagger 0, was this one. bj dagger, a lambda dagger, a lambda 1 dagger, operating on the empty state. And that would have a corresponding energy of Ej, whatever the final electron state was going to be, and a photon in mode lambda, created here, and a photon in mode lambda 1, created there. That would give us a non-zero matrix element, but that term would actually correspond to photon emission. Remember, we started out with a photon in this mode, and we seem to have ended up also with a photon in some other mode. Well, with a starting energy that was just E1 plus h bar omega lambda 1, the delta function argument in Fermi's golden rule is the following. But this cannot be close to 0 because Ej minus E1 has to be greater than or equal to 0. J can only be 1 or 2. And this photon energy is also a positive number. So there's no way that this delta function argument here can equal 0. So this state, although it would have a finite matrix element, if we start out with the electron in state 1 and a photon in mode lambda 1, we cannot get the delta function argument to work. Hence, on integrating over time as above, this term associated with this particular final state will not give rise to any steady transition rate, because it's forbidden by the energies not working out in the delta function. Hence, this possible final state can be discarded, at least when starting with the initial state we were looking at. Simply put, we cannot emit a photon here because there is no lower energy for the electron to go to. Now, this might have seemed obvious to start with, but we formally derived this conclusion here, not merely presumed that it is obvious.